today is a bunch of old exam questions. I'm going to do some mostly transaction stuff, but I will try and squeeze in a clocks and memory question while we're about it. So here's one. It's about programmer Tony, who implements 3 transaction processes, P, Q, and R, in our usual little language of locks, assignment, and sequential composition. So we're reminded, note that if one process holds a lock on a variable, other processes must wait to read, write, or lock that variable. And we're also told initially that x is 20, y is 30, and z is 10. And then we're asked to identify what might happen in a bunch of situations. So let's figure it out. Okay, let's have a look at the processes first. You'll notice that process P locks x and y around the outside, and then it modifies x and y. In particular, it looks like y is giving x 5. Everyone see that? Okay, so this is good news. If you've got locks round the outside for all the variables which are being changed, what that means is that the transaction is atomic. That's to say, you can treat it as a single action, right? Because its locks make sure that nobody else is going to interrupt the process of modifying, in this case, x and y, while it's going on. So you can treat transaction P as a single move that transfers 5 from y to x. And similarly, you can see that Q and R are both atomic. So there's going to be no funny business about one transaction happening in between another transaction doing a read and doing a write or something like that. There's nothing funny going on, at least as far as interfering with reads and writes to memory. There might be something else funny going on though. So let's see if we can figure out what happens if P and Q execute concurrently. Okay, any suggestions? You can see that Q basically has y transferring 3 to z. Yeah? Y goes down by 3, z goes up by 3. Okay, so what's going to happen if P and Q execute concurrently?
You will get 1 second and have to wait for Q.
Well, certainly, so there's no interference with P's first step. Taking the lock on X, there's no competition for that. And then P and Q both want to take a lock on Y. So it's anybody's guess which of those two happens first. But once one of them has taken the lock on Y, the other one has no choice but to wait until that lock is released. So what that tells you is that either we're going to get all of P executing and then all of Q, or the other way around. Now, does it matter? P is Y gives 5 to X, Q is Y gives 3 to Z. Does it matter which way around they happen? No. And indeed, all of these transactions that just look like a transfer from one place to another, it usually doesn't matter what order those happen in. So it doesn't really matter whether P goes first or Q goes first. We're going to get the same outcome either way, and that is just that X gets an extra 5, so we'll end up with X is 25. Y will have given away 5 in one transaction and 3 in the other, so Y will have given away 8 altogether, and will end up being 22. And Z will have collected 3. So Z will go up to 13. Is everybody fine with why that's the right answer for part A? Yeah? If not, it'd be a good time to shout. Okay? And there's no problem about, there's no chance of deadlock because because P and Q only have one lock in common. So it's not like, I mean, P locks X, but Q doesn't care about X. Q locks Z, but P doesn't care about Z. So they have to take turns, but they're not going to get stuck. That's the key thing. Okay, what happens if Q and R execute concurrently? Again, starting from the same point of X is 20, Y is 30, Z is 10. What will X be? Uh, 18. Right, you can see what's happening is Y is giving 3 to Z, and X is giving 2 to Z. Lucky old Z. So X ends up being 18, Y ends up being 27, and Z has collected another 5, Z goes up to 15. Okay, same situation. Q and R have only one lock in common. Whichever one locks Z first will go first, will do its transaction first, and it doesn't matter which way around they happen. There's no danger of getting stuck. Okay, fine. How about part C? We get, so this time it's 2 copies of R executing concurrently. So R and another process exactly like it execute concurrently. In R you can see X gives Z2. So what's going to happen? Z's going to get 4. X is going to give Z2 twice, which means X is going to end up being 16, Y is going to stay being 30, and Z is going to end up being 14. Is there any danger of deadlock? No, because both copies of R will start by trying to lock Z, and whichever one gets that lock first, the other one will wait. They're taking the same locks, but they're taking the same locks in the same order, so that means they're doing the right thing to take turns with each other. Rather, they're not in any danger of getting stuck. Okay, how about part D? What if all 3 of P, Q, and R execute concurrently? And note there's 2 marks for this, which might mean that there's more than one possible thing that might happen.
You can get deadlock?
Yes, they can deadlock. How do they deadlock?
If P locks X, Q locks Y, then R locks Z.
Yeah, if they all take their first lock, then each of them is waiting for a second lock that somebody else holds. They can't release the lock they already hold until they're finished, but they can't get the next lock they need. So they're stuck. So deadlock is one possibility. Better zoom out a little. But of course, deadlock is only a possibility. It's never an inevitability. So they might all run to completion. If they do, what's going to happen? Well, X will go up 5 and down 2. So that means X will go up in a total of 3. y will go down 5 and down 3, so y will end up being 22. And z will go up 3 and up 2, so z will end up being 15. So both of those are possible. So this is a simplified version of a classic puzzle presented by the computer scientist Professor Tony Hoare, actually Sir Tony Hoare these days. This is the problem of the dining philosophers, where you've got a bunch of people sitting around a table, and they like to think a lot, but they occasionally get hungry. They each have a bowl of rice in front of them, but they have, to eat the rice, they've only got one chopstick in between each person. It makes you wonder why they don't just eat with their fingers if they're that unconcerned about hygiene. The point is that eating with one chopstick is pretty tricky, so you need both chopsticks. The procedure for eating is to pick up one of the chopsticks next to you, then pick up the other one, then eat a bit, then put both chopsticks down. And the question is, how do you ensure that they don't starve? Because there's the danger that if everybody picks up the chopstick to their left, then they're just waiting to pick up the next chopstick, and they're never going to get to eat. So, I mean, this is a real problem when operating systems are managing resources, is the danger of deadlock. And it requires some sort of discipline about how to manage it. Anyway, so that's the reason why it's programmer Tony. It's because Tony Hoare, who basically invented about half of computer science in the 1970s, and is still absolutely razor sharp. I saw him last week. He's a top guy, brilliant man. This is his puzzle. All right, let's see what the time is. Good, plenty of time. Let's do a